Hey everyone, this is Maths Guy channel here. Today we're going to be solving power functions. So in the previous videos we've done linear, so x raised to the 1, so raised to some power is squared, the quadratic, cubic, family polynomials, the square root, 1 over 2, the truncus -1, that sort of thing. And today, so the power functions is x raised to the power of p over q, where p and q are both positive rational numbers. So a rational number is a number it's expressed as a ratio. So for the square root function, for example, the p value would be 1 and the q would be 2, and the cube root function you can see that the same thing, the same pattern here. So q is 3. So pattern here is that x raised to the power of p over q, the same as cube root of x raised to the power of p. So it's already a little bit abstract, but in essence, there's a polynomial part, so like the x squared and x cubed. There's also a root part here, so like the squared and the cube root of function. And these are just some statements here. So for example, if p is greater than q, then the polynomial will influence the function more because this part will be greater than 1. And if it's the reverse, it'll be between 0 and then the root part will dominate because between 0 and 1. And if p and q are the same, then it's just a linear equation f of x equals x. And it states that if p and q are both positive rational numbers, then 0, 0 and 1, 1 will always be on the graph. So if we were to just draw this out, so f of x equals x raised to the p over q. Okay, so here we've set p and q as the same value, 1 and 1, and hence we have the function f of x. And say for example, if I change to 2, it's quadratic, because 2 divided by 1 is still 2, and if I go 3 or any of the other integers you've seen before, so even something like 7 or like 5, you still have the similar pattern of the odd power raise. So our purposes, we're going to be going on to positive rational numbers. In another video I might cover negatives, so what happens, so for example like -1 here, you still get the hyperbola as per usual. So for example, if we have a case where p is greater than q, so p, as I know here, see like even here, it doesn't exist. The function doesn't exist anymore, simply because the negative properties of the function. So you get some very interesting graphs when p is you can get some really interesting values in the functions. So squared, kind of looking a bit like a cubic already. It also shows that for certain values you're not going to have a negative aspect to it. So that's if p is greater than q, and if q is greater than p, so that the graph is splitting in half here. Like more interesting thing here, you see like it flips like here or here. And the same as per usual. So I think it's more helpful if I express it easier. So next example, we have x raised to the 2 over 3. So the power is 2 over 3. So we'll set p as 2 and q as 3. There we go. Okay, so first of all, so it'll be the cube root of x squared. You can see here that you can't. The first thing you notice is that all the values here are all like so the domain is real, and the range is including 0 to positive infinity. And so the change thing around, so make the power 3 over 2, for example. So like that. So cube root, the square root of x cubed. There's no negative values here, so the domain is only 0 to infinity, and 0, and the range is 0 to infinity. And you don't have any negative values. For example, if we sub x is -1, we're asking what is the square root of the cube root of -1, and when you multiply a negative value by an odd amount of times, so by itself an odd amount of times, so -1 times -1 times -1, it's still -1. And when you get a square, when you square root -1, you don't get a real number. Yeah, and I've referenced the number I, but that's talking about the complex plane. And for the purpose of these videos, we probably don't need to. It won't be that useful. We won't be using it. Yeah, and you have noticed that no matter what numbers I change here, I mean, assuming p is positive and stuff, all the functions always go through this one. If I just drew 1, 1. Okay, yep, just label it. All these functions are always going through that, and 0, 0 won't matter actually. If I keep it as positive, like you see that all these functions are always going through these two particular points. Which kind of makes sense, because when we think about, we're not moving the graph left and right. There's no translation on it. There's no h or k, and also like technically there's no dilation. Because this is a power rather than a coefficient in front of the x. And yeah, that'll be all.